So loops, those are new. They weren't flown before. We'll do a stall turn, and this time we'll do it differently because we'll come out tail first. So the other stall turns would turn around at the peak. This hurricane is a fast backward flying cycle, essentially. So now we're going to do stationary rolls and stationary flips. And these are actually some of the hardest maneuvers. And the reason for that is that when you're flying in just a kind of a confined space, the helicopter is fighting its own airflow. And tic-tocs, again, are also some of the most difficult maneuvers for the same reasons. And we'll stop with the inverted hover. Okay, so thanks. So that looks very nice, but did it actually fly what we wanted to? So let's verify that. So the white helicopter is the target trajectory, and the black helicopter is the replay of what we just flew. And you'll see that they're pretty close, actually. And the position accuracy is essentially 1 to 2 meters. And that's even while flying under really high g-forces and high speeds. And it's, I mean, depending on what you think, you might think 1 or 2 meters is really good or not so good. But it's very, very good in this case. And if you ask a human pilot to fly this air show with an accuracy of 1 meter, they'd probably think you're crazy. And so it stays really close throughout the entire trajectory. Okay. So let's take a look at another maneuver. So this is called auto rotation. And this is an emergency maneuver that you might perform if your engine dies or if your tail rotor dies. And the idea here is that if your engine dies, it'd be nice to not lose the entire helicopter. And when your tail rotor dies, your engine might still be working, but your helicopter will start pirouetting uncontrollably, essentially. And in order to land it safely, you have to shut off the engine anyways. And so when you switch off the engine and you try to land safely, essentially what you're trying to do is you're trying to maintain high blade speed while you're high in the air in this area, and then you try to slow down the blade speed as you get closer. And so there's 3 phases in auto rotation landing, and this area up here where you try to keep the high blade speed is called glide. When you try to slow down, it's called the flare, and then there's the landing. And the way the landing works is essentially you hope that by the end of the flare you're close enough to the ground to where you can just fall. And if you didn't do that right, then there's nothing you can do at that point. Okay, so this requires a different dynamics model. And as you might imagine, it's hard to worry about the blade speed if you have no idea what it is. And so the new dynamics model is going to actually introduce the blade speed, which we'll represent as omega here. And it just adds some terms to the dynamics model that depends on that. And so perhaps the most important is this one here. So before, this term was simply the collective control. And now we multiply it by the blade speed, right? So if your blade speed is low, then the collective has less of an impact. And that makes sense, right? I mean, now before your engine was actually running, and so it didn't matter because you could actually control the engine, and now you can't do that anymore. So the blade speed matters now. And so if you assume that the collective will have the same effect as it would at a high blade speed, you'd be in for quite the surprise, and you'd crash. And again, we do the exact same thing as before. We collect the same kind of data. There's no difference in the data collection. There's no difference in the learning of this model. It's still a simple linear regression. All that changes is that we added a few parameters. So here's how well this works. And so this is just showing you essentially the same thing I showed you before with the giant errors. It actually works pretty well in this case. And so the solid line is the simulation, and the dashed line is the flight data. And this is how well we can predict the blade speed. So we concluded from this that this was kind of good enough on its own to try some auto rotation landings. So let's see that. This is the glide phase. And now it's flaring. And it lands. And this will loop a couple times, but just so you have some idea, we repeated this 35 times, and it was successful all 35. So is this kind of luck, or are we controlling this, or what's going on here? So let's see how accurately we were actually controlling the blade speed. So what we did here, while you're doing the glide, you can't avoid losing some blade speed as you fall. So what we do is we set a target of roughly 1150, and we set some target forward velocities and downward velocities, and we want to keep the helicopter level. And we see that the controller is actually very good at keeping it at that rate. At that blade speed. So what are some current directions with this work? So the work I described to you, one of the limitations was that every time you want to fly something new, you probably have to provide you 4 or 5 demonstrations of it. So can we do better? So let's say we have the pilot fly a 20-meter stall turn, and a 30-meter stall turn, and a 40-meter stall turn, and a 50-meter stall turn. At that point, can we ask an algorithm to give us a 25-meter stall turn, or a 35-meter stall turn, or a 22, or 27, or anything in between? And some preliminary work here actually shows us that you can, in fact, do that for trajectories that are close enough. And what happens is we input kind of these 5 demos, 20, 30, 40, 50, and we ask you for anything in between, and it outputs a target trajectory and a dynamics model that are good enough to fly. And the accuracy of these isn't going to be the same 1 to 2 meter. It's kind of more 2 to 3 meter, but it's still very, very good. So it's going to be better than just flying one of the 20 or 30 or 40 meter stall turns that you have in your library. Essentially, the answer is if you don't have the data, you can do better. It's better if you can collect the data and ask the pilot to fly these trajectories. But if you don't have it, we can design an algorithm that can do better. And so here's an example of a parameterized maneuver. And this is probably the most difficult helicopter maneuver that humans fly. And so it's called the chaos, for a good reason, in my opinion. And the helicopter pirouettes in place while flipping at the same time. And so to me it's kind of amazing that it even stays in the air while doing this. But in this case we've even parameterized it by yaw rate. And so we can say we want it to pirouette at a rate of 1 pirouette per second, and it'll generate a chaos that we can fly. Or we can say 1.5 pirouettes per second, and it'll generate a chaos that we can fly. So in summary, our approach leverages multiple expert demonstrations to, first off, infer a target trajectory, and second, learn better models along that trajectory for control. And this enabled extreme aerobatics at the level of an expert human pilot. And so now we can hopefully talk about how this might be applicable to the work that you're interested in. Thank you.